You are not moving. That is what the body reports. The floor is solid. The air is still. Nothing pulls at you, nothing pushes. If you close your eyes, the only evidence of motion is the slow rise and fall of your own breathing, and even that is barely a disturbance. You are, by every measure the body has, perfectly at rest. You are moving at 1,670 kilometers per hour. You are moving at 107,000 kilometers per hour. You are moving at 828,000 kilometers per hour. You are moving at approximately 1,300,000 kilometers per hour, relative to the oldest light in the universe. All four of those are happening right now, simultaneously, in different directions. They have been happening every moment of your life. You have never, not once, in all the time you have been alive, been still, and you cannot feel any of it. Hello, and welcome to Sidereal. Tonight we are going to spend some time with a question that sounds simple on the surface and gets stranger the further you follow it. How fast are you moving through space right now? Not in a general sense specifically. The actual numbers, what they mean, and why something moving at those speeds leaves no trace whatsoever on the body that is doing the moving. Before we begin, if this kind of slow exploration is useful to you for sleep or winding down, a like or a subscribe genuinely helps the channel. And I am curious where you are listening from. Drop your location and the time in the comments. Now, here is the question tonight is really asking. The body is a precision instrument. It detects heartbeats, footsteps, the change in temperature when someone opens a door. How does it fail, completely and without exception, to detect 1 million kilometers per hour? The answer was worked out, in pieces, by a series of people across 4 centuries, and the last piece required a satellite, a team that worked for 15 years, and a measurement so precise it could detect a temperature difference of 0.003 of a degree across the entire sky. Tonight goes through all of it. The 4 layers of motion, how each was discovered, and the single physical principle that explains why none of them can be felt. For now, you are lying still, and the planet beneath you is spinning. The man who made Earth's rotation visible did not go looking for a way to prove Copernicus right. He was a physicist and instrument maker who had been working on pendulums for years, and who had noticed, while experimenting in his workshop in Paris in 1851, that a pendulum set in motion resisted being tilted, that the plane of its swing held steady even when you tried to rotate the supporting frame. The pendulum did not care about the frame. It was anchored to something larger. He followed that observation to its conclusion, and on the 8th of January, 1851, he suspended an iron ball on a wire 67 meters long from the dome of the Pantheon and invited a small group of scientists to watch. The ball swung, and slowly, over the hours that followed, the plane of the swing rotated. The floor moved beneath the pendulum. The building, the street, the city, all of it turning under a weight that simply hung there, indifferent to the motion of the ground. Léon Foucault sent a note to the scientists before the demonstration. It read, "You are invited to see the Earth turn." The invitation was not a metaphor. The pendulum's plane of swing, held fixed by inertia relative to the distant stars, remained while the building rotated beneath it. In Paris, at the latitude of 48.8 degrees north, the floor completed one apparent rotation in about 32 hours. At the poles, it would complete a rotation in exactly 24 hours, because at the poles, Earth's rotation is most directly visible as a turning of the floor beneath a fixed pendulum. At the equator, the effect would vanish entirely. The pendulum would appear not to rotate at all, because at the equator there is no component of Earth's rotation aligned with the vertical that produces the turning of the swing plane. This matched the mathematics precisely. Foucault had not invented a demonstration of what theory predicted. He had built a window through which the rotation became directly observable, with nothing more than a wire, a weight, and patience. The demonstration was conducted publicly at the Pantheon in February of 1851, before an audience that reportedly included members of the public as well as scientists. The reaction was described at the time as one of silent awe, people standing and watching the floor slowly separate from the plane of the pendulum swing, the physical reality of the Earth's rotation made visible without instruments or mathematics, simply by watching. Napoleon III was shown the demonstration. Foucault was subsequently invited to install a pendulum at the Paris Observatory and received the Legion of Honor. At the equator, the surface of the Earth moves at approximately 1,670 kilometers per hour. This follows directly from the geometry. The circumference of the Earth at the equator is 40,075 kilometers. The planet completes one full rotation every 23 hours, 56 minutes, and 4 seconds, a period astronomers call the sidereal day, measured not against the Sun but against the distant stars. Divide the circumference by that time and you arrive at just under 465 meters per second, 1,670 kilometers per hour. The speed varies depending on where you are standing. At mid-latitudes, New York, London, Tokyo, Sydney, the surface is moving at roughly 1,200 to 1,275 kilometers per hour. The Earth is widest at the equator and narrows toward the poles, so each point on the surface traces a smaller circle in the same amount of time. The formula is simple. Take the equatorial speed and multiply by the cosine of your latitude. At the poles themselves, the speed is 0. A person standing at the South Pole would simply be turning in place, the planet rotating beneath their feet once every 23 hours and 56 minutes, with no change in their position relative to the ice. 1,670 kilometers per hour is faster than the speed of sound in air, which is approximately 1,225 kilometers per hour at sea level. A person standing at the equator is, relative to a fixed point in space, moving faster than the sound of their own voice could travel. You do not feel this. The air around you, the buildings, the ground under your feet, the atmosphere itself, all of it moves with you at the same speed, in the same direction. There is no wind, there is no resistance, there is nothing for your body to push against, and nothing pushing back. The body only detects change: the lurch of a starting train, the tilt of an accelerating car, the brief pressure of a corner taken too fast. Steady speed leaves nothing to detect. The inner ear, which is the body's primary motion sensor, responds to acceleration and deceleration, to spinning up and spinning down. It has no mechanism for measuring velocity that does not change. And Earth's rotation, for any human lifetime, does not change in any way the body can register. There is a small subtlety worth naming. The sidereal day, 23 hours, 56 minutes, 4 seconds is the true rotation period of the Earth, measured against the background stars. The solar day, the 24 hours we use for clocks and calendars, is slightly longer. The reason is that as the Earth rotates, it is also moving along its orbit around the Sun. By the time it has completed one full rotation relative to the stars, it has also moved slightly along that orbit enough that it needs to rotate a little further before the Sun is back in the same position in the sky. That extra rotation adds roughly 4 minutes to each solar day. Over a full year, those 4 minutes accumulate to one complete extra rotation, which is why a year contains 366 sidereal days rather than 365. This distinction between the sidereal day and the solar day was not obvious to early astronomers and took considerable effort to resolve. It matters because the sidereal day is the physically meaningful quantity, the actual rotation rate of the Earth relative to space. The solar day is a practical convenience, adjusted to keep noon aligned with the Sun's highest point in the sky. When measuring Earth's rotational speed in the context of its motion through space, it is the sidereal day that is relevant. The Earth's rotation is also gradually slowing. The tidal interaction between the Earth and the Moon transfers angular momentum from the Earth's rotation to the Moon's orbit, which means the Earth's rotation decelerates very slowly over time and the Moon gradually spirals outward. The day is currently lengthening by approximately 1.8 milliseconds per century. This is a real effect, confirmed by analysis of ancient eclipse records, growth rings in fossil corals, and direct laser ranging from the surface of the Moon, a technique that became possible after the Apollo missions left retroreflectors at the landing sites. The number is small. It does not affect tonight's figures to any meaningful precision, but it means that 4.6 billion years ago, when the Earth was new, the day was closer to 6 hours long. The planet was spinning at roughly 4 times its current rate. The equatorial surface speed was closer to 6,000 kilometers per hour. It is worth sitting with how strange this is from the body's point of view. The inner ear contains the vestibular system, 3 semicircular canals filled with fluid, oriented in 3 perpendicular planes, that detect rotation and two otolith organs that detect linear acceleration and the direction of gravity. This system is exquisitely sensitive. It can detect the rotation of your head by a few degrees. It can detect the gentle acceleration of an elevator beginning to rise. It is the reason you can balance on one foot with your eyes closed, and the reason a sudden movement in a vehicle registers instantly before you have consciously processed it. It is one of the oldest sensory systems in the animal kingdom, present in some form in nearly every creature with a backbone, and it detects nothing of the Earth's rotation. The reason is that the semicircular canals respond to angular acceleration to changes in the rate of rotation, not to steady rotation itself. The Earth's rotation is, to an extraordinary degree, steady. It does not speed up or slow down on any timescale the body could register. Once the fluid in the semicircular canals has settled into the steady rotation, there is nothing further to detect. If the Earth were to suddenly double its rotation rate, the body would feel it intensely for a moment, until the new rate became steady and the sensation faded. But the rotation has been at its current rate for the body's entire life, and for the entire life of every ancestor the body descends from. There has never been a transient to detect. The rotation has one further consequence worth naming before leaving this layer behind. It produces a force that shapes the weather, the oceans, and the orbits of satellites above the atmosphere. It is called the Coriolis effect, after Gaspard Gustave de Coriolis, a French mathematician and engineer who described it rigorously in 1835. The principle is this: any object moving freely across the surface of a rotating body, a cannonball, a wind current, a mass of cold air moving toward the equator, appears to be deflected from a straight path, because the ground beneath it is rotating. In the northern hemisphere, the apparent deflection is to the right. In the southern hemisphere, to the left. The Coriolis effect is why tropical cyclones rotate counterclockwise in the northern hemisphere and clockwise in the south. The rising warm air over the ocean begins to spiral as it moves outward from the center of low pressure, and the Coriolis force determines which direction the spiral turns. It is also why the large-scale circulation patterns of Earth's atmosphere, the trade winds, the prevailing westerlies, the polar easterlies blow in the directions they do. Without the rotation, and without the Coriolis force it produces, the climate of the planet would be unrecognizably different. The rotation also shapes Earth's geometry. The centrifugal effects of rotation have caused the Earth to bulge at the equator and flatten at the poles over the billions of years since the planet formed. The equatorial radius is approximately 6,378 kilometers. The polar radius is approximately 6,357 kilometers, a difference of about 21 kilometers. A person standing at the equator is roughly 21 kilometers further from Earth's center than a person standing at either pole. The equatorial bulge affects spacecraft. A satellite in a tilted orbit, one that passes over higher latitudes, experiences an asymmetric gravitational pull from the bulge, which causes the plane of the orbit to precess slowly around Earth's axis. Satellite engineers can use this deliberately. By choosing the right orbital altitude and inclination, they arrange for the orbit to precess at exactly the rate needed to keep it aligned with the direction of the Sun throughout the year. Weather satellites and Earth observation satellites often use these sun-synchronous orbits because they see the same illumination angle on every pass over a given location, useful for tracking environmental change over time. All of this, the Coriolis effect, the equatorial bulge, the orbital precession, follows from the rotation at 1,670 kilometers per hour. The body lying in the dark feels none of it as motion, but the planet shows it in its shape, its weather, and the orbits of the machines placed above it. The Foucault pendulum in Paris, a reconstruction, the original suspension cable having broken in 2010, still swings under the dome of the Pantheon, and the floor still rotates slowly beneath it, and anyone who goes to watch it can see the Earth turning with their own eyes. The demonstration works every time. The physics has not changed since 1851 and will not change. 1,670 kilometers per hour. That is the innermost layer of tonight's motion. The next layer does not step gently upward. The orbit of the Earth around the Sun runs at 107,000 kilometers per hour, 64 times faster than the rotation at the equator. And establishing that the orbit was real, rather than theoretical, took one astronomer in Essex, 2 years of confusion, and a wind vane on the Thames. In the autumn of 1725, James Bradley pointed a telescope at the sky above Wanstead in Essex and waited for a star to betray the Earth. The star was Gamma Draconis, a bright, relatively nearby star in the constellation Draco that passed almost directly overhead at the latitude of London, which made it ideal for the measurement Bradley intended. He was hunting stellar parallax. The principle of parallax is the same principle your two eyes use to estimate distance. Different viewing angles produce slightly different apparent positions, and the difference in angle tells you how far away the object is. Applied to stars, the parallax shift caused by Earth's orbit should make nearby stars appear to shift very slightly against the distant background as Earth moves from one side of the Sun to the other across the year. The existence of any measurable shift would prove, directly and observationally, that Earth was orbiting the Sun at a meaningful speed. The size of the shift would tell you how far away the star was. Bradley was working with Samuel Molyneux, a wealthy amateur astronomer, who had funded and equipped the instrument they were using, a specially constructed vertical telescope mounted in Molyneux's house and designed to measure very small angular positions with exceptional precision. The design minimized the kinds of instrumental errors that had plagued earlier attempts to measure parallax. They had reason to be confident in the setup. They found a shift. But it was wrong. A parallax shift caused by orbital motion produces a specific pattern in time. The maximum apparent displacement of Gamma Draconis should have occurred in June and December, the points in Earth's orbit where the planet's motion is most directly toward and away from a star in that part of the sky. But Bradley and Molyneux found that the maximum displacement was occurring in March and September, 3 months out of phase with what parallax required. The direction of the displacement was also subtly wrong relative to what parallax would produce. They measured through the autumn of 1725 through 1726, observing with care and ruling out instrumental error one by one. The shift was consistent, it was repeatable, it was unambiguously real, and it made no sense in terms of parallax. Molyneux died in April of 1728, having spent more than 2 years with this problem, without finding its resolution. Bradley continued alone, adding more stars to his observing program. The same 3-month phase offset appeared in all of them. Whatever was causing the shift was not a property of Gamma Draconis. It was a property of Earth's relationship to incoming starlight in general. The answer came to Bradley on the Thames. In the spring of 1728, he was on the water. The accounts do not specify the occasion, and he noticed that the vane at the top of the mast was not pointing directly into the true wind. It was pointing into the apparent wind, a combination of the actual wind direction and the direction of the boat's motion. Each time the boat changed course, the vane shifted, not because the wind itself had changed, but because the direction of the boat's motion had changed, altering the composite direction from which the air appeared to arrive. Light behaves the same way. A telescope is a tube, and a tube has a finite length. By the time an incoming photon has traveled from the objective lens at the top of the tube to the eyepiece at the bottom, the Earth has moved slightly because the Earth is always moving. To catch the photon at the eyepiece, the tube must be tilted very slightly in the direction of Earth's motion, just as an umbrella must be tilted forward in the direction you are walking if you want to keep the rain off in still air. The faster you are walking, the more you must tilt. The faster Earth is moving relative to the incoming light, the greater the tilt required. And because Earth moves in a roughly circular orbit, constantly changing direction, the required tilt direction changes throughout the year, tracing out a small ellipse in the sky. The maximum tilt in any given direction is not reached when Earth is farthest from the star. It is reached when Earth's velocity is most directly perpendicular to the line of sight to the star. This produces a phase relationship that is exactly 90 degrees offset from parallax, which is precisely the 3-month offset Bradley had been measuring without understanding. This is stellar aberration. It is not a measurement of the star's position, it is a measurement of the observer's velocity. Bradley had spent 2 years measuring the speed of the Earth's orbit, in the form of the angle by which starlight must be deflected to catch it in a moving telescope, without knowing that was what he was doing. The angle of aberration Bradley measured was approximately 20.5 arcseconds. That angle is the arctangent of the ratio of Earth's orbital speed to the speed of light. If you know the angle and you know the speed of light, you can calculate Earth's orbital speed. If you know the angle and you know Earth's orbital speed, you can calculate the speed of light. Bradley's measurement did both simultaneously. It confirmed old Romer's earlier estimate of the speed of light, which had been made from the timing of Jupiter's moons in 1676 and had not been universally accepted, and it confirmed the orbital speed of the Earth. He announced the discovery to the Royal Society in a letter to Edmond Halley, published in 1729. The French astronomer Jean-Baptiste Joseph Delambre, who catalogued the astronomical discoveries of the 18th century, called it the most brilliant and useful of the century. That was a century which included a great deal of useful astronomy. The judgment was not modest, and it was not wrong. Bradley had been looking for evidence of position. He found evidence of velocity. The universe handed him a different proof than the one he had set out to collect. One more thing about what Bradley did not find. He went looking for stellar parallax, the position shift that would prove Earth orbits the Sun by triangulation, and never detected it. The reason is that stars are much farther away than 18th century astronomers imagined. Parallax produces tiny angles at stellar distances, and Bradley's instrument, despite its precision, was not sensitive enough to detect them. Stellar parallax was not successfully measured until 1838, when Friedrich Bessel observed the star 61 Cygni shifting by just over 0.3 of an arcsecond across the year. That shift is roughly 60 times smaller than the aberration Bradley measured. The parallax was there all along, buried below the noise floor of every instrument pointed at the stars before Bessel's. The story of how that number was established is, in its way, the story of how science actually proceeds not by a single decisive stroke but by a confused measurement, a long period of not understanding it, and a chance observation in an unrelated setting that suddenly makes everything fall into place. Earth orbits the Sun at an average speed of approximately 107,000 kilometers per hour, just under 30 kilometers per second. The orbit is almost circular, with an eccentricity of 0.0167, meaning the difference between closest and farthest approach to the Sun amounts to about 5 million kilometers across an orbit that averages 149.6 million kilometers in radius. At perihelion, closest approach in early January, Earth moves slightly faster than average. At aphelion, farthest point in early July, slightly slower. The variation across the year is modest, a few thousand kilometers per hour, and plays no role in anything the body can detect. The full circumference of Earth's orbit is approximately 940 million kilometers, traveled in 365.25 days. This requires the 107,000 kilometers per hour the orbit delivers. The aberration of starlight that Bradley measured is the same for every star in the sky. The maximum angular displacement is always approximately 20.5 arcseconds, regardless of which star is being observed. What differs between stars is not the amplitude but the shape of the ellipse. The aberration traces over the year, which depends on the angle between the star's position and Earth's orbital plane. A star exactly perpendicular to the orbital plane traces a circular aberration ellipse. A star in the plane of the orbit sees the ellipse collapse to a straight line. Its apparent position shifts back and forth along a single axis rather than tracing an ellipse. Stars at intermediate angles trace ellipses of intermediate eccentricity. Bradley observed enough stars at enough positions on the sky to verify that these geometric predictions were satisfied precisely. The shape and size of each star's aberration ellipse matched the predictions as a function of that star's position on the sky. This level of internal consistency was what transformed a puzzling observation into a confirmed physical discovery. A single anomalous result is a curiosity. Dozens of anomalous results that all obey the same mathematical pattern, with the variation in each case matching exactly the geometry of the situation, constitute evidence of a different kind. The orbit was not a number estimated from theoretical considerations. It was a number measured across the entire sky, and the measurement came back the same everywhere. There is a further elegance in what the aberration reveals. Bradley's measurement is essentially a statement about the ratio of two speeds. Earth's orbital speed divided by the speed of light produces an angle. The speed of light was known approximately 300,000 kilometers per second, as Romer had established, and so the orbital speed followed directly. But the relationship works the other way too. If you are an observer with no prior knowledge of the speed of light, and you measure the aberration angle and know the orbital speed from independent means, you get the speed of light. The two measurements are locked together by geometry. Each one is a check on the other, and Bradley's observations provided one of the earliest independent confirmations that Romer's estimate of light speed was in the right territory. It would take another century and much more precise instruments before the speed of light was nailed down with precision, but Bradley's aberration was part of the chain. There is also a subtlety in how aberration differs from parallax that is worth holding for a moment, because it illuminates something about the difference between position and velocity as physical observables. Parallax depends on where the Earth is in its orbit. The displacement of the Earth from one point in the orbit to another changes the viewing angle to a nearby star. It is a measurement of position change. Aberration depends on how fast the Earth is moving and in what direction it is the velocity of the Earth, not the position, that determines the direction the telescope must be tilted. Two completely different measurements, both detectable in principle from the same telescope pointed at the same star, but sensitive to different physical quantities, one to position, one to velocity. That Bradley found the velocity signal but not the position signal, and that the velocity signal was itself the wrong signal he was looking for, is one of the more charming accidents in the history of measurement. The fastest crewed vehicle humans have ever built achieved a speed of approximately 39,897 kilometers per hour. The Apollo 10 command module during its return from the Moon in May of 1969. Earth's orbital speed is nearly 3 times faster. The universe has been carrying you faster than the fastest thing humans have ever built, in every moment of your life, without your noticing and without your having any way to notice. The orbit is the second layer. The third is 8 times larger still, and establishing it required not a wind vane and a river, but globular clusters. A young woman at Harvard cataloguing variable stars in the Magellanic Clouds, and a man from Missouri who chose astronomy because the journalism school hadn't opened yet. Harlow Shapley was born in November of 1885 on a farm near Nashville, Missouri, the second of 5 children. He left school early to work as a newspaper reporter, then returned to education at a small preparatory school and eventually enrolled at the University of Missouri, intending to study journalism. The journalism school had not yet opened. He needed a course and scanned the university catalogue, looking for somewhere to start. He later said he picked the first subject he could actually pronounce, which turned out to be astronomy. Astronomy coming before archaeology. Archaeology being something he could not say without effort. Whether this is exactly true is not certain. What is certain is that he arrived at the subject by accident and stayed with it for the rest of his life. He went to Princeton for his graduate work, then to the Mount Wilson Observatory in California, where beginning in 1914 he had access to what was then the most powerful telescope in the world first, the 1.5-meter reflector, and later the 2.5-meter Hooker telescope, which held that distinction until the Palomar 200-inch telescope was completed in 1948. He turned the instruments toward globular clusters. A globular cluster is a roughly spherical collection of stars, anywhere from tens of thousands to more than 1 million, held together by their mutual gravity and orbiting the galaxy as a unit in a halo that surrounds the galactic disk. They are ancient objects. Many of the stars within them formed when the universe was less than 2 billion years old. Because they orbit the galaxy in 3 dimensions, spread above and below the disk, their distribution on the sky reflects the overall shape of the galactic halo, and therefore, Shapley reasoned, the position of the galactic center. Of the roughly 100 globular clusters known at the time, about 1/3 lay within the region of the constellation Sagittarius. They were not evenly distributed across the sky. They were concentrated in one direction. If globular clusters orbited the galaxy in a roughly spherical halo centered on the galactic nucleus, then the concentration of clusters told Shapley which direction the nucleus was and its angular position in the sky. Getting the distance required a method. Shapley had 2. The first came from Henrietta Swan Leavitt, who had been working at the Harvard College Observatory since 1902. Leavitt's formal role was as a human computer. She was paid to examine photographic plates and catalogue the brightness of stars, the work considered routine enough that the institution of the time did not feel it warranted professional scientific credit. Between 1908 and 1912, while cataloguing variable stars in the small Magellanic Cloud, She noticed a precise relationship between the period of Cepheid variable stars, stars that pulsate in brightness on regular cycles of days to weeks, and their intrinsic luminosity. The longer the period, the more luminous the star. The relationship was tight enough that if you measured a Cepheid's period, you knew its absolute brightness. Comparing that absolute brightness to its apparent brightness in the sky gave the distance. Leavitt published her finding in 1912 in a paper that noted the relationship in plain terms and made no particular claim for its significance. The significance was recognized by others. The Cepheid period luminosity relation became the most important distance measuring tool in astronomy for the following decades, and it was built on the work of a woman whose salary was 25 cents an hour and whose name was rarely attached to the tool she created. Shapley used Cepheids and a second class of variable star, the variable stars known as R Lyrae, which follow a similar but calibrated relationship, to measure the distances to as many globular clusters as he could. He obtained distances ranging from a few tens of thousands to more than 200,000 light-years. He plotted their three-dimensional distribution, located the centroid of the system, and in a letter to Arthur Eddington in January of 1918, he reported what the data showed. The galactic center was in the direction of Sagittarius, at a distance of approximately 50,000 light-years from the Sun. The Sun was not near the center of the galaxy. It was a long way from the center, in the outer regions of a system far larger than anyone had imagined. The accepted model before Shapley, developed by Jacobus Kapteyn based on star counts, had placed the Sun near the center of a galaxy roughly 30,000 light-years across. Shapley's galaxy was 10 times larger, and the Sun was displaced far from its middle. He later wrote, "It was a shocking thought, this sudden realization that the center of our universe was not where we stood but far off in space." Copernicus had moved the Earth from the center of the solar system. Shapley moved the solar system from the center of the galaxy. The two displacements belong to the same sequence, each one relocating the human position to somewhere less central than the previous picture had assumed. Each one arrived not through philosophical argument but through measurement. Each one was resisted, then accepted, then absorbed into the standard picture so thoroughly that it became difficult to imagine anyone had ever believed otherwise. Shapley's distance estimate was wrong. The galactic center is approximately 26,000 light-years from the Sun, not 50,000. His Cepheid calibration had a systematic error. The Cepheids he was using were a class called Type II Cepheids, which are intrinsically less luminous than the Type I Cepheids Leavitt had calibrated. Shapley did not know this distinction existed. Additionally, dust in the galactic plane absorbs starlight, making distant objects appear fainter and therefore more distant than they are. Both effects pushed his distance estimate too high. The structural conclusion that the Sun is far from the galactic center and that the center lies in the direction of Sagittarius was correct. The number needed revision. The revision came in stages across the following decades, and the precise measurement of how fast the solar system orbits the galactic center required instruments that did not exist until the 21st century. The Gaia satellite, launched by the European Space Agency in December of 2013, was designed to measure the positions and motions of more than 1 billion stars across the Milky Way with unprecedented precision. In 2016, a team led by Jason Hunt at the Dunlap Institute for Astronomy and Astrophysics at the University of Toronto used early Gaia data combined with radial velocity measurements from over 200,000 stars in the solar neighborhood, determine the solar system's orbital speed around the galactic centre. The method is indirect and worth understanding. They were not measuring the Sun's speed directly, they were looking for a gap. In the distribution of stellar velocities in the solar neighborhood, there is a deficit of stars with nearly zero angular momentum around the galactic center. Stars with nearly zero angular momentum travel on radial orbits that take them through the galactic nucleus. They are not in stable circular orbits like the Sun, but on highly eccentric paths. The speed at which this deficit occurs in the velocity distribution tells you how fast the reference frame of the solar neighborhood, the Sun included, is moving around the center. The result was 239 plus or minus 9 kilometers per second, 828,000 kilometers per hour. One galactic orbit at that speed takes between 225 and 250 million years. The range reflects genuine uncertainty in the mass distribution of the Milky Way, which affects how the orbital period relates to orbital speed. Since the solar system formed, approximately 4.6 billion years ago, it has completed roughly 20 orbits. The most recent completed one ended somewhere around 225 to 250 million years ago, when the late Triassic period was ending and the first dinosaurs were establishing themselves on land. The supercontinent, Pangaea, was still intact. There were no flowering plants, no birds, no grasses. Mammals had just appeared small, probably nocturnal, unrecognizable as mammals by any feature that word now calls to mind. 2 galactic years ago, the Ordovician period, marine life dominant, the land largely bare rock. The entire history of complex animal life on Earth represents approximately 2.5 galactic orbits. Through all of that, the solar system has been sweeping around the galactic center at 828,000 kilometers per hour, through the first forests, the first reptiles, the great extinctions, the rise and fall of the dinosaurs, the small and terrified mammals that survived the impact 66 million years ago and eventually, over the following tens of millions of years, produced something capable of looking up and asking how fast it was moving through all of it. The galactic orbital speed continued, unchanged, unacknowledged, carrying everything along. The structure of the Milky Way that Shapley was trying to map is now considerably better understood than it was in 1918. The galaxy is a barred spiral, a flattened disk of stars, gas, and dust with a pronounced bar-shaped structure at the center, from which 2 major spiral arms and several minor ones wind outward. The disk is approximately 100,000 light-years in diameter. The total number of stars is estimated at between 100 billion and 400 billion, with the uncertainty reflecting the difficulty of detecting the faintest, most distant objects. The Sun sits in a minor feature called the Orion Arm, located between 2 of the major spiral arms, at a distance of approximately 26,000 light-years from the galactic center. The spiral arms are not rigid structures that orbit intact. They are density waves, regions of slightly compressed gas and dust that move through the galaxy at a speed different from the individual stars. The solar system orbits faster than the density wave pattern moves, so over the course of its orbit it periodically enters a major spiral arm and then exits again. The star formation rate is higher in the arms, where the compressed gas triggers more frequent collapse into new stars. The solar system currently sits between arms, in a quieter region of the disk. Above and below the disk, a roughly spherical halo of older stars and globular clusters extends to perhaps 150,000 light-years from the center. Beyond the visible halo lies the dark matter halo, the vast, invisible concentration of matter that contributes the majority of the galaxy's total mass. The orbital speed of stars at large distances from the galactic center stays roughly constant, rather than declining as it would if the visible matter were all there was. The dark matter halo, extending far beyond the visible disk, provides the additional gravitational mass that keeps those orbital speeds elevated. Its total mass is estimated to be several times the mass of all the visible stars combined. The displacement Shapley introduced was, in human terms, difficult to absorb. For most of history, the assumption that the Earth and later the Sun occupied a central or near-central position had been not just a scientific belief but a comfortable one. Shapley's globular clusters dissolved it. The Sun was revealed to be far out in the suburbs of an enormous structure, neither central nor special in its location, one star among hundreds of billions, positioned by nothing more than the accidents of where a particular cloud of gas happened to collapse. The realization took time to settle, even among astronomers, and Shapley himself spent years defending the scale of his galaxy against colleagues who found it implausibly large. The galactic center around which the orbit runs is a compact radio source called Sagittarius A star, a supermassive black hole containing approximately 4 million times the mass of the Sun, sitting 26,000 light-years away. It was identified as a radio source in 1974 by Bruce Ballack and Robert Brown using the Green Bank Interferometer in West Virginia. Its nature as a supermassive black hole was confirmed over subsequent decades through measurements of the orbits of stars near the galactic center, stars that can only be moving as fast as they are observed to move if there is an enormous concentration of mass at the center of their orbits. The Event Horizon Telescope produced the first direct image of its shadow in 2022, a ring of hot gas curving around a dark center, the most distant object ever directly imaged. The solar system does not orbit Sagittarius A star specifically, the way a planet orbits a star. It orbits the entire gravitational field of the galaxy, all 400 billion visible stars, all the gas and dust in the disk, and the vast dark matter halo that extends far beyond the visible disk and may contain several times more mass than everything that emits light. Sagittarius A star is the marker for the galactic center, not the sole source of the orbital force. 828,000 kilometers per hour. Third layer. The fourth requires the oldest thing in the universe, a light that has been traveling since 300,000 years after the Big Bang, currently at a temperature just barely above absolute zero, filling the sky in every direction. Getting to the measurement of our motion against that light requires first understanding why two physicists in a basement in Cleveland in 1887 found nothing at all when they tried to measure Earth's motion through space, and why that nothing turned out to be one of the most important results in the history of physics. Albert Michelson was 35 years old in 1887 and had already built the most precise optical instrument of his era. He was, by every account, a craftsman in the deepest sense, someone for whom the construction of the measuring device was as much a matter of craft as whatever the device measured. He had performed a version of the experiment in Berlin in 1881, and the result had been inconclusive. When he took a position at the Case School of Applied Science in Cleveland, Ohio, he found a collaborator in Edward Morley, a chemist at Western Reserve University next door, a man with the patience and the practical skill to help him build something considerably better than what he had in Berlin. What they were looking for was the luminiferous ether, a medium that 19th century physicists were almost universally confident must exist. The argument was by analogy. Sound is a wave. Waves require a medium to propagate through. They are disturbances in something physical. If you remove the medium, the wave cannot travel. Seismic waves are disturbances in rock and earth. Ocean waves are disturbances in water. Sound waves are disturbances in air. Light is also a wave. This was established by James Clerk Maxwell's work on electromagnetism in the 1860s, which showed that light is an oscillation of electric and magnetic fields propagating through space. But unlike sound, light seemed to travel through vacuum, through the space between the stars, where there was apparently nothing to disturb. The solution most physicists found satisfying was that space was not empty, that it was filled with a medium, the ether, so rarefied as to be otherwise undetectable, through which light propagated the way sound propagated through air. If the ether existed and was stationary, fixed in space, unmoving, then the Earth moving through it at approximately 30 kilometers per second should create an ether wind, in the same way that driving a car with the window down creates a wind on a still day. Light traveling against this wind would be slowed slightly relative to light traveling with it, and light traveling perpendicular to the ether flow would be affected differently still. An interferometer, a device that splits a beam of light along two perpendicular paths, reflects it back from mirrors, and recombines the two beams, would detect this difference as a shift in the interference pattern when the device was rotated, because the two arms of the interferometer would present different travel time paths to the light, depending on their orientation relative to the ether wind. Maxwell himself had noted, in correspondence in 1879, that the expected effect was very small. It depended on the square of the ratio of Earth's orbital speed to the speed of light, which is a very small number. He thought it might be beyond what instruments of the time could measure. Michelson's instrument was designed to solve that problem. The interferometer Michelson and Morley built in Cleveland floated on a large stone slab supported on a bed of mercury, which isolated it from vibrations in the building and the street, and allowed it to be rotated smoothly during measurements. The light path was extended by reflecting the beam back and forth between mirrors multiple times, increasing the effective length of each arm and therefore the sensitivity to any speed difference. The instrument was capable of detecting a fringe shift of 1/100th of the expected signal, meaning it was 20 times more sensitive than the measurement required. The expected shift from Earth's orbital speed alone was approximately 0.4 of a fringe. The instrument could detect down to 0.02. The experiment was conducted in the basement of Pierce Hall at the Case School over several days in July of 1887. The slab was rotated continuously throughout the measurements. The measurements were taken at different times of day, at different orientations of the apparatus, to rule out any systematic error from a fixed direction. They looked for the variation in fringe pattern that the ether wind should produce. They did not find it. The maximum observed fringe shift was 0.02 within the limits of measurement noise. The average was smaller still. Michelson and Morley's report to the American Journal of Science, published in November of 1887, stated the result with characteristic directness. The experiments on relative motion of Earth and ether have been completed, and the result is decidedly negative. Michelson considered the experiment a failure. He had built the most precise optical instrument in the world for a specific purpose, and the instrument had found nothing. He continued to believe the ether must be there. He continued for years to look for it. He never found the expected signal. What the null result implied was not immediately clear to anyone who encountered it. The natural response, the response Michelson himself held for years, was that the instrument must be wrong, or the ether must be organized differently than assumed, or that some compensating factor was hiding the signal. The result was reproducible, repeated by other groups in subsequent years with different apparatus and at different locations, always finding the same absence. The signal was not hidden, it was not there. If the ether did not produce a detectable wind, there were two possibilities. Either the ether moved with the Earth was dragged along by it, the way air inside a sealed vehicle moves with the vehicle, or the ether did not exist. The idea that the ether was dragged along by the Earth created its own problems. It made predictions about the aberration of starlight that contradicted Bradley's measurements, because a dragged ether would change the apparent direction of incoming light in ways that were not observed. The experiments pointed in one direction. Nobody wanted to follow. The situation was intellectually uncomfortable in a way that is worth holding for a moment. 19th century physics was a successful and coherent system. Maxwell's equations for electromagnetism, Newton's mechanics, thermodynamics, all of it worked. All of it produced precise predictions that matched experiment. The ether was not an eccentric speculation. It was a logically required component of the theory as it stood. And yet the most sensitive measurement ever made of Earth's motion through the ether found nothing. Physics was confronted with a result it could not assimilate without breaking something. What had happened was not that the instrument had failed. The ether did not exist. Or, stated more carefully, there was no medium through which light propagated that was stationary relative to anything. Light was not a disturbance in a material substrate. It was an electromagnetic oscillation that propagated through empty space at a fixed speed, and that fixed speed was the same for all observers, regardless of their motion. This was the result nobody had expected, and nobody, at first, knew what to do with. If the speed of light is the same for all observers regardless of their relative motion, then the relationship between space, time, and motion that Newton's physics assumed cannot be correct. Newton's physics assumed that space and time were fixed, absolute, the same for all observers, the stage on which motion played out. If the speed of light is constant for all observers, that assumption has to go. George Fitzgerald in 1889 proposed that objects moving through the ether contracted slightly in the direction of motion, which would make the travel times of light along the two interferometer arms appear equal even if the ether existed. Hendrik Lorentz worked out the mathematics of this contraction more fully and showed that it was consistent with the null result. The contraction factor, now called the Lorentz factor, is a function of the ratio of the object's speed to the speed of light. At everyday speeds, it is vanishingly small. As an object approaches the speed of light, the contraction becomes extreme. These proposals kept the ether alive, but only by adding a mechanism with no independent physical explanation. The contraction was invented to account for the null result, not derived from any prior theory. It was the kind of move physicists make when they are trying to preserve a framework that the experiments are undermining. The situation in physics in 1905 was that the best available theory involved an ether that could not be detected, producing contractions that had no physical explanation, preserving a framework that the experiments were steadily undermining. Albert Einstein's paper on special relativity in June of that year began from a different starting point. He discarded the ether entirely. He proposed two postulates: that the laws of physics are the same in all inertial frames of reference, and that the speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the source. From those two postulates, the consequences followed by pure logic. If the speed of light is constant for all observers, time itself cannot be constant. A moving clock runs slower than a stationary one, not because of any mechanical effect, but because time itself passes at a different rate for observers in relative motion. A moving object is shorter in the direction of motion than it would be at rest, not because it is being compressed by the ether, but because length and time are both aspects of a four-dimensional space-time geometry that changes with relative motion. Two events that appear simultaneous to one observer may not appear simultaneous to another observer in relative motion, because simultaneity, like length and duration, is not absolute. These are exact results, not approximations. They are confirmed by a century of experiments, by the lifetimes of cosmic ray muons that arrive at Earth's surface despite having too short a half-life to survive the journey at non-relativistic speeds, by the precision of the satellite navigation systems that must account for relativistic time dilation to maintain their accuracy, by the decay rates of particles in accelerators traveling at speeds close to the speed of light. The effects are negligible at the speeds of ordinary life. At speeds approaching light, they become extreme. The ether was not just undetected, it was unnecessary. The universe has no preferred frame of reference, no fixed medium against which absolute motion can be measured. There is only motion relative to other things. Michelson won the Nobel Prize in Physics in 1907 for his optical precision instruments. He remained, until the end of his life, somewhat troubled by the implications of his own result. He had found nothing when he expected something. Physics took that nothing and rebuilt its understanding of space and time on top of it. The experiment that Michelson considered his greatest failure turned out to be the experiment that made the modern picture of motion possible. The Michelson-Morley experiment has been repeated in increasingly precise forms for more than a century since. Modern versions use lasers, optical cavities, and atomic clocks rather than the mirrors and interference fringes Michelson worked with, and they have pushed the precision of the null result to extraordinary levels. The best modern experiments confirm that the speed of light is independent of direction to within a few parts in 10 to the 18th, a precision millions of times finer than Michelson achieved. Every one of these experiments finds the same thing Michelson found: no variation, no ether wind, no preferred direction. The speed of light is the same in every direction, for every observer, to the limits of what can be measured. The null result that Michelson considered a failure has become one of the most thoroughly confirmed facts in all of physics. The experiment also stands as a particular kind of lesson about what counts as a discovery. There is a tendency to think of discovery as the finding of a thing, a new planet, a new particle, a new force. But some of the most important discoveries in the history of science have been discoveries that a thing is not there. Michelson and Morley discovered the absence of the ether. The absence was more consequential than almost any presence could have been, because it forced a reconstruction of the concepts of space and time themselves. A measurement that comes back empty is not always a failed measurement. Sometimes the emptiness is the result. There is a certain justice in that arc. Michelson set out to measure a property of the universe, the velocity of the Earth through the ether, and the result was that the thing he was trying to measure did not exist. What he actually measured, without recognizing it as such, was the invariance of the speed of light. The fact that no matter how you orient the apparatus, no matter which direction the Earth is moving, light travels at the same speed. That invariance is the cornerstone of all modern physics. The measurement that felt like failure was the measurement that mattered most. The physical principle that explains why none of the four speeds can be felt was not discovered by Einstein and not by Michelson. It was worked out by Galileo in the 1630s from a thought experiment about a ship, and it was, at the time, a deeply dangerous idea. Galileo Galilei was born in Pisa in 1564 and spent most of his productive life dismantling the received physics of his era, not through dramatic proclamations but through the patient practice of looking at what things actually do rather than what they were supposed to do. According to Aristotle, who had been the authority on the behavior of matter for nearly 2,000 years and was, on several points that mattered enormously for the question of Earth's motion, Wrong. Aristotle's physics had a foundational premise that felt obvious and was incorrect. Rest is the natural state of earthly objects. A stone placed on the ground stays there because staying is its nature. A cart pushed across a field stops when the pushing stops because the motive force has been removed. Motion requires a continuous cause. Remove the cause and the motion ceases. This matched experience well enough to be convincing for 2 millennia, because in the everyday world, friction and air resistance are always present, and they do cause moving things to stop. Aristotle took the observation and made it a principle, without recognizing that what he was observing was not the physics of motion itself, but the physics of motion in the presence of friction. The implication for a rotating Earth was direct and, within Aristotle's framework, decisive. If the Earth were rotating, spinning at some significant speed, then anything not physically attached to the ground would be left behind as the ground moved under it. A stone dropped from the top of a tower would fall while the tower moved eastward beneath it, and would land to the west of the tower's base. A cannonball fired eastward would carry farther than one fired westward, because the Earth would be moving away from the eastward ball and into the westward one. A bird in the air would find, on launching from a branch, that the branch had moved while it was airborne. None of these effects was observed. Therefore, the Earth was not rotating. The argument was used against Copernicus, and against anyone who proposed a moving Earth. It was used confidently, because within the Aristotelian framework it was logically sound. The problem was with the framework. Galileo presented his answer in the dialogue concerning the 2 chief world systems, published in 1632. The critical passage is presented through a character named Salviati, who proposes a thought experiment set below decks on a large ship moving smoothly through a calm sea. The passage is worth following in some detail, because the argument is careful and the conclusion is exact. Salviati asks the reader to imagine going below decks with a friend, bringing flies, butterflies, and small flying creatures, a bowl of water with fish in it, and a bottle that drips water into a vessel below. The ship is set in motion at whatever speed you like, provided the motion is steady and not fluctuating. Now observe, the flies fly equally in all directions, the fish swim equally in all directions, the drops fall from the bottle into the vessel below exactly as they would if the ship were still. Throwing a ball to your friend requires no more force in one direction than another. The drops do not accumulate toward the stern of the vessel, as they would if the ship's motion were carrying the vessel forward beneath them. You cannot, by any mechanical experiment conducted below decks, determine whether the ship is moving or standing still. The logic is precise. Everything inside the ship is already moving with it before the experiment begins. The air, the water, the flies, the fish, all of it shares the ship's velocity. When a fly launches itself from one wall toward the other, it is not leaping from a stationary surface into the ship's motion. It begins already moving with the ship, at the ship's speed, and the crossing from wall to wall happens on top of that shared velocity. The ship's motion adds nothing to the flight of the fly and subtracts nothing from it, because the fly shares the motion completely. There is no relative motion between the fly and the air around it. Everything inside the frame moves together, and so the frame's motion is invisible to everything inside it. This is the principle of inertia stated not as a law, but as a practical truth derived from reasoning about experience. A body in uniform motion does not advertise its motion to anything sharing that motion. The question, am I moving, cannot be answered from inside a closed system traveling at constant velocity, because constant velocity and rest are, for mechanical purposes, identical. Galileo had identified what Aristotle missed. The natural state of a body is not rest. The natural state is continuation. Whatever the body is already doing, it continues doing, unless something acts on it. What requires a cause is not motion but change of motion. Constant velocity requires no force. Acceleration, changing speed or direction requires a force and produces an effect the body can detect. But pure, steady motion, nothing. This inversion of the Aristotelian premise was complete and radical. It was also, in the context of 1632, deeply political. The dialogue was published with official church approval, but that approval had been obtained under conditions the Inquisition subsequently decided were inadequate. Galileo had been warned in 1616 not to hold or defend the Copernican view. The dialogue, which conducted a comparison between the Copernican and Ptolemaic systems and made the answer fairly clear, was deemed a violation. He was summoned to Rome in 1633. He was 68 years old, in poor health, and made the journey. He was tried by the Inquisition, found guilty of having held and defended the opinion that the earth moves, and made a formal recantation in a public ceremony. He was sentenced to house arrest at his villa in Arcetri, outside Florence, where he remained for the last 8 years of his life. The dialogue was placed on the Index of Forbidden Books, where it remained until 1835. It continued to circulate in manuscript copies and in a Latin translation published in Strasbourg in 1635. The physics did not care about the index. It was correct regardless of what the Inquisition decided. There is an earlier moment that shows how fully Galileo had absorbed his own principle. In 1624, years before the dialogue was published, he wrote a long reply to a letter by Francesco Ingoli, who had argued against the Copernican system on precisely the physical grounds that a moving Earth should produce observable effects that were not observed. Galileo addressed, among other things, the experiment of dropping a rock from the top of a ship's mast. Ingoli's camp claimed that observers had performed this and seen the rockland behind the mast displaced westward by the ship's eastward motion. Galileo replied that the rock lands at the base of the mast. He added, with the particular sharpness he used for people he considered to be lying, "I have been twice as good a philosopher as those others, because they, in saying what is the opposite of the effect, have also added the lie of their having seen this by experiment. And I have made the experiment." He had done it. He already knew the answer from the physical reasoning, and he had confirmed it. The rock falls at the base of the mast because it is already moving with the ship when it is released. It carries that motion through the fall. There is no force to separate it from the ship's velocity. It arrives at the deck precisely where the base of the mast is, because the base of the mast has moved at exactly the same speed, in exactly the same direction, through the same fall. The principle Galileo identified has a formal name it was not yet given in 1632, the principle of relativity. In its most general statement, the laws of physics are the same in all inertial reference frames, all frames moving at constant velocity relative to each other. No mechanical experiment conducted inside a closed, uniformly moving system can reveal that the system is moving. The physics inside Galileo's ship below decks is identical to the physics in a ship at rest. There is no measurement, no observation, no experiment that distinguishes them. Nothing in the physics prefers one velocity over another. There is no physical concept of being at rest that is more fundamental than moving at constant velocity in any direction. The implications of this principle extend far beyond the question of Earth's motion. They reach into the nature of space and time itself. If the laws of physics are identical in all inertial frames, and if one of those laws is that light travels at a fixed speed, then the fixed speed of light cannot be different for different observers. It has to be the same for all of them, regardless of their relative motion. And if the speed of light is the same for all observers, then the relationship between space and time that Newton assumed, with time ticking at the same rate for everyone, distances being the same for everyone, cannot be correct. Time must pass at different rates for observers in relative motion. Lengths must differ. Simultaneity must be relative rather than absolute. These are not paradoxes or failures of understanding. They are the logically necessary consequences of two facts: that the laws of physics are the same in all inertial frames, and that the speed of light is the same for all observers. Galileo arrived at the first premise: the laws of physics are the same in all inertial frames from reasoning about a ship. He did not arrive at the second, the constancy of light speed, because the tools to measure or reason about it precisely did not exist in 1632. That step was taken 3 centuries later, after Michelson and Morley found nothing in their basement in Cleveland. But the second follows from the first. Once the behavior of light is correctly understood, the ship in the dialogue is the seed from which special relativity grows, planted 300 years before the tree appeared. Isaac Newton formalized the principle in 1687 as the first of his 3 laws of motion. A body remains in uniform motion in a straight line unless acted upon by an external force. Rest is not special. Rest is one value of velocity, the value 0, and the physics does not give it any priority over any other value. A body moving at constant velocity is, for every mechanical experiment conducted within its frame, identical to a body at rest. This is why the body lying in the dark feels nothing, not because its instruments are inadequate, because constant velocity is physically indistinguishable from rest. There is nothing to detect. The Earth's rotation, the orbit around the Sun, the galactic motion, all of it is either constant velocity or sufficiently close to constant that the accelerations involved are far below any biological threshold. The body sits in its frame and reports. Still, Galileo knew in 1632 why that report, while correct within its reference frame, does not tell the whole story. The principle extends beyond mechanical experiments. Einstein's special relativity showed in 1905 that it applies to light as well, that no optical experiment conducted within an inertial frame can detect the frame's motion. This is what Michelson and Morley demonstrated, negatively, in 1887. They could not measure Earth's motion through the ether because the ether did not exist, and the speed of light was the same in every direction regardless of Earth's motion. Galileo's ship, extended to include electromagnetic phenomena, is still Galileo's ship. The result is a universe in which constant velocity, at any speed, is invisible from inside the frame doing the moving. 1,300,000 kilometers per hour, in 4 directions at once, and nothing, almost nothing, because the universe contains one reference that is not arbitrary, not chosen by the physicist, but defined by the structure of the universe itself. And that reference was found, by accident, by 2 men in New Jersey who were trying to remove a noise from an antenna. In the autumn of 1964, Arno Penzias and Robert Wilson had a noise problem. Penzias was 31 and had been at Bell Laboratories in New Jersey for 2 years. Wilson was 28 and had arrived from Caltech, where he had done his graduate work in radio astronomy. They had been assigned to a large horn-shaped antenna at the Holmdel facility, a device originally designed and built in 1960 for communications with the first active communication satellites, the Echo balloon satellites that reflected radio signals from one ground station to another. By the time Penzias and Wilson arrived, the communications function had been superseded and the antenna was available for radio astronomy. It was an exceptional instrument, sensitive, precisely calibrated, free from many of the noise sources that plagued other antenna designs of the era. They had intended to use it for careful measurements of radio emission from the halo of the Milky Way, a research program that required them to map the background noise of the antenna precisely so they could subtract it from whatever galactic emission they found. To do that, they needed to account for every source of noise in the system. They expected certain amounts of noise from the electronics, from the atmosphere, and from the antenna structure itself. What they found was more noise than they expected, coming equally from every direction they pointed the antenna, at a level that did not vary with time or direction. They worked through the possible explanations. A known radio source somewhere in the sky, ruled out, because the signal was isotropic, the same in every direction. Radio interference from New York City, visible on the horizon, ruled out, because the signal did not vary with the city's position. Interference from the radar at a nearby military installation, ruled out similarly. Radiation from the nuclear tests that had been conducted in the atmosphere, considered and rejected. They found pigeons. 2 pigeons had been roosting inside the horn antenna and had coated the interior surfaces with what Wilson later described in a published paper as a white dielectric material. They trapped the pigeons, cleaned the antenna, and sent the pigeons by mail to a Bell Labs facility in Whippany, New Jersey, where they were released. The pigeons, apparently finding Holmdel more congenial, returned. They were eventually, and with some reluctance on the part of the researchers, removed permanently. The antenna was cleaned again. The noise was still there. At this point, Penzias learned of a paper being prepared by a group at Princeton: Robert Dick, Jim Peebles, Peter Roll, and David Wilkinson, who were building a small radio antenna on the roof of the Palmer Physical Laboratory to search for exactly the kind of radiation that Penzias and Wilson had been picking up. The Princeton group had reasoned that if the universe had begun in a hot, dense state and had been expanding and cooling ever since, the radiation from the earliest period should still be detectable as a faint, cold glow of microwave radiation filling the sky uniformly. They were building an instrument to look for it. They had not yet made the measurement. Penzias called Dick. Dick hung up the phone, turned to his colleagues and said, "Boys, we've been scooped." The 2 groups published simultaneously in the Astrophysical Journal in 1965. the Princeton group providing the theoretical interpretation, and the Bell Labs group reporting the measurement. Penzias and Wilson received the Nobel Prize in Physics in 1978. Their Nobel citation described the discovery as the most important measurement made in the history of astronomy. What they had found was the cosmic microwave background, the thermal afterglow of the early universe. When the universe was approximately 300,000 years old, it had cooled enough that the fog of plasma filling all of space finally became transparent. Before that moment, photons could not travel freely. They were scattered almost immediately by the dense sea of electrons, like light in a thick fog. When the electrons combined with protons to form neutral hydrogen atoms, the scattering stopped, and the photons streamed freely in all directions. They have been traveling ever since, filling the universe, losing energy as the universe expanded, cooling from the thousands of degrees they had when they were released to the 2.7255 Kelvin. They are now just barely above absolute zero. The cosmic microwave background is the oldest light there is. It is the boundary of the visible universe. We cannot see beyond it, because beyond it, in the direction of the early universe, lies the opaque plasma that even light could not penetrate. Everything we see in the night sky, every star, every galaxy, every quasar, is between us and this background. It is the last thing before the beginning. Penzias and Wilson measured it as uniform in every direction, isotropic, the same temperature everywhere they pointed the antenna. This was consistent with a universe that had begun hot and uniform, and had been expanding uniformly. The context in which this measurement landed was a debate that had been running in cosmology for nearly 2 decades. The Big Bang model that the universe began in an extremely hot, dense state and has been expanding and cooling ever since was not universally accepted. The competing theory, developed by Fred Hoyle, Hermann Bondi, and Thomas Gold in the late 1940s, was called the steady-state model. In the steady-state picture, the universe had no beginning. It had always existed and looked roughly the same at all times. New matter was created continuously throughout space, at a rate too slow to be detectable to fill in the gaps left by expansion, keeping the average density constant. The universe, on this account, was eternal and unchanging in its large-scale properties. It had no hot beginning and therefore no afterglow. Fred Hoyle, who was among the most brilliant theoretical astronomers of the 20th century, had coined the phrase Big Bang in a radio broadcast in 1949. He intended it as a dismissive label for an idea he found physically absurd. The label stuck and lost its dismissive edge. Hoyle continued to dispute the Big Bang interpretation of the evidence until late in his life. He was wrong, but he was wrong carefully and productively, in ways that forced the Big Bang's proponents to make the model more precise and more testable. The cosmic microwave background settled the debate. The steady-state model had no mechanism for producing a uniform, isotropic background of microwave radiation filling the entire sky. The Big Bang model predicted it not as an afterthought, but as a central consequence of the hot, dense beginning. The radiation was there. It was uniform. It had the spectrum of thermal radiation from a body at a temperature close to 3 Kelvin, and it was filling the universe in every direction. There was no room for a steady-state explanation. The debate was effectively over in 1965, though Hoyle and a small group of collaborators continued to propose alternative interpretations for several decades. The cosmic microwave background represents a boundary in the history of the universe. On this side of the boundary, 14 billion years of expansion and cooling, the universe is transparent, and light travels freely from source to observer across cosmic distances. On the other side, before recombination, the universe was opaque. Every photon emitted in the hot plasma was immediately scattered by free electrons, unable to travel more than a short distance before being absorbed and re-emitted in a new direction. The universe was full of light, but that light was trapped, the way light is trapped inside the dense plasma of a stellar interior. The cosmic microwave background is the afterglow of the moment the trap opened, the moment the plasma cooled into neutral hydrogen and the photons were freed to travel. Everything we can observe in the sky sits between us and this wall of last scattering. Every star, every galaxy, every quasar, all of them formed after recombination in the transparent universe. The background is the last thing before the beginning of the observable universe in time. It is the oldest light there is, and it fills the sky in every direction, completely and uniformly. because the surface of last scattering surrounds us equally in every direction we sit inside it, at the center of our own observable universe, seeing the past in every direction we look. The uniformity that Penzias and Wilson found, and the precision with which it has been measured since, established one of the most important and puzzling facts in modern cosmology. The universe, at the time of last scattering, was extraordinarily smooth. The temperature was the same in every direction to 1 part in 100,000. This level of uniformity presents a significant challenge. Regions of the sky that appear to be in thermal equilibrium with each other are so far apart that if the universe had expanded from the Big Bang in a straightforward way, they could never have been in causal contact. No signal could have traveled between them fast enough to equalize their temperatures. The explanation most cosmologists accept involves a period of extremely rapid expansion in the earliest moments of the universe, a period called inflation, which would have taken a small, causally connected region and expanded it to encompass the entire observable universe, smoothing out any initial irregularities in the process. The cosmic microwave background's uniformity is one of the central pieces of evidence for this model. The cosmic microwave background also serves as a kind of clock, or at least a thermometer that reads the age of the universe. The temperature of the background is tied directly to how much the universe has expanded since the light was released. When the photons were freed at recombination, the universe was at a temperature of roughly 3000 Kelvin, hot enough to glow a dull red, like the surface of a cool star. Since then, the expansion of the universe has stretched the wavelength of those photons by a factor of approximately 1100, which has lowered their temperature by the same factor, from 3000 Kelvin down to 2.7255. That stretching factor is a direct measure of how much the universe has grown since the light was released. The universe is now about 1100 times larger, in linear scale, than it was when the cosmic microwave background was emitted. This gives the background a peculiar dual nature. It is, on the one hand, the most distant thing we can see emitted at the edge of the observable universe, from the surface of last scattering 13.8 billion years ago. And it is, on the other hand, present everywhere, passing through every point in space at every moment, including the room you are in. It is both unimaginably far away in time and origin, and completely local in its presence. The photons reaching a detector tonight left the surface of last scattering at a particular distance, but identical photons are passing through every cubic centimeter of every room on Earth, having traveled comparable distances from all directions. The background is not a thing in one place. It is a condition of all of space, a faint thermal glow that fills the universe and that everything moves through. But the uniformity could not be perfect. The galaxies, the clusters, the vast filamentary structures that make up the large-scale universe today, all of these had to have grown from something. Gravity amplifies density differences over time, but there had to be density differences to amplify. The cosmic microwave background, if examined precisely enough, should show the tiny fluctuations in temperature, 1 part in 100,000, that corresponded to the slightly overdense and underdense regions of the early universe from which all subsequent structure grew. The fluctuations were too small for Penzias and Wilson to detect with their antenna. Detecting them required a satellite. That satellite was still 25 years in the future. But before the fluctuations, there was something else in the background, a larger, more immediately detectable departure from uniformity that was not a property of the early universe at all. It was a record of our own motion. When an observer moves toward a source of light, the light is blue-shifted, its wavelength compressed, its frequency increased, its energy slightly higher. When the observer moves away from the same source, the reverse. Red-shifted, longer wavelength, lower frequency, lower energy. This is the Doppler effect, familiar from the way a police siren rises in pitch as it approaches and drops as it passes. It applies to thermal radiation, including the cosmic microwave background, just as it applies to sound and to visible light. If you are moving through the cosmic microwave background, moving through a field of ancient light that fills the sky with equal intensity in every direction, then the hemisphere of sky you are moving toward will appear very slightly warmer than the hemisphere you are moving away from. The photons arriving from the direction you are heading toward have been slightly blue-shifted, making them appear as warmer radiation. The photons arriving from behind you have been red-shifted, making them appear cooler. The difference in temperature between the two hemispheres, for any given speed of motion can be calculated exactly from the Doppler formula. This pattern, warmer in one direction, cooler in the opposite, transitioning smoothly between, is called a dipole because it has one warm pole and one cool pole. It was predicted before it was measured. The first rough detection of the dipole was made in 1969 by Edward Conklin at Stanford using a ground-based microwave radiometer. Conklin found a signal consistent with a velocity of several hundred kilometers per second in a direction roughly toward the constellation Leo, but the measurement was too noisy to be precise. Better measurements followed over the next decade, including work by Corey and Wilkinson in 1976, each adding precision to the amplitude and direction. But the definitive measurement, the one that established the dipole's precise amplitude, direction, and physical interpretation beyond any reasonable doubt, came from a satellite. The Cosmic Background Explorer was launched from Vandenberg Air Force Base in California on November 18, 1989, aboard a Delta rocket. It weighed approximately 2,200 kilograms and carried 3 science instruments into a polar orbit approximately 560 miles above Earth. The satellite was designed to address 3 questions. What is the precise spectrum of the cosmic microwave background? What is the large-scale temperature distribution of the background across the entire sky? And what is the intensity of the infrared background at wavelengths where galaxies emit most of their light? The instrument responsible for measuring the spectrum was the Far Infrared Absolute Spectrophotometer, led by John Mather. Its purpose was to determine whether the background radiation truly followed the blackbody spectrum, the characteristic thermal distribution that only a system in complete thermal equilibrium produces. If the background was a perfect blackbody, that would confirm that the universe had been in thermal equilibrium in its early phase, as the Big Bang model required. If the spectrum deviated from a perfect blackbody, it would imply additional energy sources or processes that the standard model did not account for. The result was definitive. The spectrum of the cosmic microwave background, as measured by the Far Infrared Absolute Spectrophotometer, matched a perfect blackbody at a temperature of 2.7255 Kelvin, with a precision that no previous measurement had approached. The fit was so tight that on the graph presented at the American Astronomical Society meeting in January of 1990, when John Mather displayed the data alongside the theoretical curve, the audience gave a standing ovation. Error bars were not visible. The data and the curve were indistinguishable to the eye. It was the most precisely measured natural spectrum in the history of science at the time of its measurement. The instrument responsible for mapping the temperature distribution was the differential microwave radiometers, led by George Smoot of the Lawrence Berkeley National Laboratory. Smoot had submitted his first proposal for a satellite to measure the cosmic microwave background to NASA in 1974. The proposal was rejected. He submitted revised versions over the following years. The mission was eventually approved, and the instrument designed, built, calibrated, and launched across a span of 15 years. During that time, other groups came close to detecting the temperature fluctuations Smoot was looking for with balloon-borne instruments, keeping the scientific pressure high and the timelines tight. The satellite collected data from 1989 to 1993. The differential microwave radiometers measured the temperature difference between widely separated points on the sky in 3 frequency channels chosen so that foreground emission from the Milky Way, which is strongest at low frequencies, could be identified and subtracted from the cosmological signal. The first thing that emerged from the temperature maps was the dipole, enormous and unmistakable. The largest signal in the data after the Milky Way foreground was removed. The sky in the direction of Leo was warmer than the sky in the direction of Aquarius, with a smooth gradient between them, exactly as predicted for an observer moving at several hundred kilometers per second. The amplitude of the dipole corresponds to a temperature difference of approximately 3.36 millikelvin 0.003 of a Kelvin between the warmest and coolest points. That temperature difference corresponds to a speed. The relationship between the dipole amplitude and the observer's velocity follows directly from the Doppler formula. The velocity of the solar system relative to the cosmic microwave background works out to approximately 369 kilometers per second, directed toward a point in the constellation Leo at coordinates right ascension 11 hours and 20 minutes, declination -7 degrees. The uncertainty on this measurement is less than 1 kilometer per second, 369 kilometers per second, 1,329,000 kilometers per hour. After the dipole was identified and subtracted from the data, a computational step that removed the signature of our own motion, setting it aside, the intrinsic temperature fluctuations of the cosmic microwave background became visible. These were the primordial seeds of structure. Temperature variations of approximately 30 millionths of a Kelvin, corresponding to density fluctuations in the early universe from which all subsequent structure grew. The fluctuations were present at the 1 part in 100,000 level, as theoretical models had predicted, patterned on angular scales from large to small, in a way that told physicists about the composition and geometry of the early universe. Smoot announced this discovery at a press conference on April 23, 1992. He said, in front of cameras and journalists, "If you are religious, it is like seeing the face of God." The remark attracted attention. The discovery attracted more. The Cosmic Background Explorer results were published in the Astrophysical Journal Letters and became one of the most cited papers in the history of astronomy. George Smoot and John Mather received the Nobel Prize in Physics in 2006, Smoot for the temperature anisotropy measurement, and Mather for the spectral measurement, confirming the blackbody nature of the cosmic microwave background. Smoot died on September 18, 2025. The speed of 369 kilometers per second in the direction of Leo is not purely the galactic orbital speed. It is the net motion of the solar system relative to the cosmic microwave background frame, incorporating all the velocities stacked on top of each other. The galactic orbital speed is approximately 230 kilometers per second, directed around the galactic center. The Milky Way has a peculiar velocity relative to the local group. The local group has a peculiar velocity relative to the larger structures surrounding it. The figure measured by the Cosmic Background Explorer is the sum of all of these, pointing in the direction that results from all the component motions combined. The Wilkinson Microwave Anisotropy Probe, launched in 2001, and the Planck satellite, launched in 2009, refined the dipole measurement further. The Wilkinson Microwave Anisotropy Probe improved on the Cosmic Background Explorer's angular resolution by a factor of roughly 30, mapping the temperature fluctuations of the background with sufficient detail to constrain the basic cosmological parameters: the density of ordinary matter, the density of dark matter, the density of dark energy, and the curvature of space to a few % precision. The dipole, being so much larger than the fluctuations, was measured with corresponding precision. The Planck satellite, with still finer resolution and better sensitivity, produced the current best maps of the background. The current accepted value for the dipole speed from Planck is 369.8 plus or minus 0.2 kilometers per second. The direction is precise to a fraction of a degree. This is among the most precisely measured velocities in all of astronomy. There is a subtlety about the dipole that has become a subject of active research in recent years, and it is worth naming honestly because it touches the frontier of what is settled. The dipole is conventionally interpreted entirely as a Doppler effect, the consequence of our motion through the cosmic microwave background. On that interpretation, if you could somehow stop the solar system relative to the background, the dipole would vanish and the sky would appear uniform in temperature. This is the standard and almost certainly correct interpretation, and it is the one tonight has used throughout. But there is a way to test it. If the dipole is purely a result of our motion, then the same motion should produce a corresponding effect in the distribution of distant galaxies and quasars objects so far away that they should be at rest, on average, in the cosmic microwave background frame. Our motion should make slightly more of them appear in the direction we are moving toward, a kinematic dipole in the counts of distant sources that should match the cosmic microwave background dipole in both direction and magnitude. Several studies over the past decade have measured this dipole in catalogues of distant quasars and radio galaxies. The direction matches the cosmic microwave background dipole well. The magnitude, in some analyses, comes out larger than the motion alone predicts. This discrepancy, if it holds up, would suggest that not all of the dipole is due to our motion, that some part of it reflects a genuine large-scale asymmetry in the distribution of matter in the universe. The question is not settled, the measurements are difficult, the catalogues are imperfect, and the statistical significance is debated. It is mentioned here not to undermine the figure tonight has built toward, but to be honest that the outermost measurement, like all measurements, sits at the edge of what is known, and the edge is still being explored. For the purposes of tonight, the standard interpretation holds, and the standard interpretation is supported by a great deal of evidence. The solar system is moving at approximately 369 kilometers per second relative to the cosmic microwave background, toward Leo. That is the number. The small remaining questions concern whether the very last fraction of the dipole has an additional cause beyond our motion, a frontier question, not a challenge to the basic result. The cosmic microwave background does not define absolute rest in the sense that Einstein's relativity eliminates there is no preferred frame, no fixed medium, no stage against which all motion is ultimately measured. What the background provides is a reference frame defined by the distribution of matter and energy in the universe at its largest scale, a frame in which the ancient light, distributed almost perfectly uniformly, is at rest. Relative to that frame, and stated as simply as possible, you are moving at 1,300,000 kilometers per hour toward Leo. That is the fourth layer. The question that sits beneath all of tonight's numbers is whether the chain of reference frames ever ends. Each speed stated tonight was stated relative to something. The rotation, relative to Earth's axis, or equivalently to the distant stars. The orbit, relative to the Sun. The galactic orbital speed, relative to the galactic center. The cosmic microwave background speed, relative to the frame in which the ancient light is at rest. At each step, the question is the same, but what is that reference moving relative to? The Sun moves relative to the galactic center, yes, but the galactic center is itself moving. The galactic center is part of the Milky Way, which is part of the local group of galaxies, which is part of the Laniakea supercluster, which is part of the observable universe, which may or may not be the full extent of what exists. Laniakea was identified and named in 2014 by a team led by Brent Tully at the University of Hawaii. The identification method was different from any used in tonight's story so far. It did not rely on direct distance measurement or spectral analysis of individual objects. It relied on peculiar velocities, the departures of individual galaxies from the smooth expansion of the universe predicted by Hubble's law. In an expanding universe, every galaxy moves away from every other at a rate proportional to the distance between them. But galaxies also have small additional motions caused by the gravitational attraction of nearby concentrations of mass. By mapping these peculiar velocities across a large volume of the local universe using a catalogue of over 8,000 galaxies with measured distances and redshifts, Tully's team traced out the flows of matter, mapping which galaxies were falling toward which concentrations of mass. The boundaries of Laniakea were defined as the surfaces where the velocity flows divided the watersheds, in the analogy the team used, where the gravitational drainage basins of different superclusters meet. The name Laniakea comes from Hawaiian, chosen in honor of the Polynesian navigators who crossed the Pacific using their knowledge of the stars. It translates roughly as immeasurable heaven. The structure is approximately 520 million light-years across, containing the mass of approximately 100 million billion suns, of which about 10% is visible matter and the rest is dark matter. The Milky Way sits near the edge of Laniakea, in a region that flows toward the center of the structure, a concentration known as the Great Attractor, located roughly 150 to 250 million light-years away in the direction of the constellations Centaurus and Norma. The Great Attractor is itself not a single object but a concentration of matter, a supercluster of galaxies, whose total mass is large enough to impart a measurable gravitational acceleration to everything in Laniakea, including the Milky Way and the local group. The Great Attractor was a genuine mystery for some years. It was identified in the 1980s through peculiar velocity surveys that found a large region of galaxies all flowing toward a common point, but the point itself lay behind the plane of the Milky Way, in what astronomers call the zone of avoidance. The dense gas and dust of our own galaxy's disk absorbs visible light so effectively that the region directly behind it cannot be observed at optical wavelengths. Something massive was pulling on the local group and on hundreds of other galaxies, and that something was largely hidden behind the band of the Milky Way. Radio observations, infrared observations, and X-ray observations, all of which penetrate the galactic dust, were used over subsequent decades to map the structure behind the dust and confirm that a genuine concentration of mass was there. Beyond Laniakea, still larger structures exist. The Shapley supercluster, approximately 650 million light-years away, is one of the most massive concentrations of matter in the observable universe and contributes significantly to the bulk flow of the local group through space. It contains dozens of rich galaxy clusters and a total mass perhaps 10,000 times that of the Milky Way. The measured flow, the 369 kilometers per second recorded in the cosmic microwave background dipole, reflects the combined pull of the great attractor, the Shapley supercluster, and the overall distribution of matter at the largest scales the measurements can probe. It is, in a sense, a single number that compresses the entire gravitational history of the local universe into a speed and a direction. Does the chain end? In the framework of general relativity and the current standard cosmological model, the cosmic microwave background provides the most universal reference available, not because it defines absolute rest, but because it is the most uniformly distributed thing in the universe, and the frame in which it is isotropic is the frame in which the universe looks the same in every direction. This is called the cosmic microwave background rest frame, and it is the reference that cosmologists use when they want to describe motion on the largest scales. But that rest frame is not the end of the chain in a philosophical sense. The question of what it is itself moving relative to runs into the boundary of what is observable. If the universe extends beyond the observable horizon, and current physics provides no reason to think the observable universe is all that exists, then there may be structures beyond the horizon that influence the large-scale flows within it. Measurements of the bulk flow of galaxies on scales of hundreds of millions of light-years have sometimes suggested flows larger than the standard cosmological model predicts, which could indicate the gravitational influence of structure beyond the observable horizon. This is an active area of research, with no settled conclusion. The chain of relative motion does not resolve in the way that Newton hoped it would. Newton was aware that his mechanics required some anchor, some concept of true rest against which true motion could be defined, and he found it uncomfortable that the anchor was not directly observable. He could define absolute rest mathematically and invoke it in his laws of motion, but he could not point to it physically. The distant stars, he noted, appeared to be at rest, but their apparent rest was not the same thing as true rest. They might all be moving together in some common direction that no observation within the solar system could detect. Newton's bucket argument was his attempt to show that absolute motion was real and physically detectable, at least for rotation. Fill a bucket with water, he said, and suspend it from a twisted rope. Release the bucket so it begins to spin. At first, the water remains flat, and still while the bucket rotates around it, the water has not yet caught up with the bucket's motion. The water's surface stays level. Then, gradually, friction drags the water into rotation with the bucket, and as the water begins to spin, its surface becomes concave, climbing the sides of the bucket. Now stop the bucket suddenly. The water continues to spin, and its surface remains concave, even though the bucket is now still, and the water is moving relative to it in the opposite sense from before. Newton's question was, what is the water rotating relative to in the moment when its surface is concave but the bucket is stationary? Not relative to the bucket is still, and the water is moving relative to it. Yet at the beginning, when the water was also moving relative to the bucket, the surface was flat. The shape of the surface does not track the water's motion relative to the bucket. It tracks something else. Newton concluded that the water's surface tracks its rotation relative to absolute space, the fixed, invisible backdrop against which true rotation is defined. The concavity is caused by the centrifugal effect of true rotation, and true rotation is rotation relative to absolute space. Ernst Mach, in the 19th century, rejected this conclusion. For Mach, the spinning water was rotating relative to the distant stars relative to all the matter in the universe taken together. The concavity of the surface, in Mach's view, was caused not by rotation relative to an invisible absolute space, but by rotation relative to the total distribution of matter in the cosmos. Inertia itself, the tendency of the water to resist being pushed into the sides of the bucket, the tendency of any body to resist a change in its motion was, for Mach, a consequence of the relationship between that body and all the other matter in the universe. Remove all the distant stars and the distant galaxies, Marx suggested, and there would be no inertia at all, and Newton's bucket would mean nothing. Einstein found Mach's idea deeply compelling, and it influenced the development of general relativity. Einstein even gave it a name, Mach's principle, and tried to build a theory in which it held. General relativity is, among other things, a theory in which the geometry of space-time, the structure that tells matter how to move and that defines what counts as unaccelerated motion, is itself shaped by the distribution of matter and energy. In that respect, it is more Machian than Newtonian. There is no fixed, immovable stage. The stage is shaped by what stands on it. But general relativity does not fully implement Mach's principle in the way Einstein initially hoped. The theory still permits solutions in which inertial frames are defined even in a universe empty of matter. A rotating observer in an otherwise empty universe would still, according to the equations, feel centrifugal effects, which is exactly what Mach's principle says should be impossible. The theory contains features of both Newton's absolute space and Mach's relational picture, without fully resolving the tension between them. The question of what inertia is ultimately relative to does not have a clean, settled answer in current physics. It is one of the genuine open questions that sits beneath the entire edifice, rarely discussed because it does not affect any practical calculation, but unresolved nonetheless. What tonight's measurement provides is not an answer to that deepest question. It provides the most useful reference currently available, the frame of the cosmic microwave background, defined by the structure of the universe at its largest observed scale. Relative to that frame, 1,300,000 kilometers per hour, toward Leo. The chain does not necessarily end there, but the measurement does. Take a breath. A real one. In the time that breath takes 4 seconds, perhaps 5, the rotation of the Earth has carried the body on this surface approximately 1.3 kilometers eastward through space. The orbit of the Earth around the Sun has carried the planet approximately 120 kilometers further along its annual path. The galactic orbit has moved the entire solar system approximately 900 kilometers around the galactic center, and the motion through the ancient light has carried the local group several hundred kilometers further in the direction of Leo. None of that is approximate in the loose sense. Those are the actual distances, derived from the actual speeds, for an actual breath. The reason none of it registers is that Galileo's principle holds across all 4 layers. Each motion is either constant velocity or so close to it the accelerations are so small and so evenly distributed that no biological instrument is capable of detecting the change. The body sits in its frame and reports. Still, the report is correct relative to the floor. The floor is correct relative to the building. The building is correct relative to the ground. At that scale, nothing is moving, and the body's instruments are adequate to the scale they were built for. But the scale of tonight's question is different. Tonight's question is about motion relative to progressively larger reference frames: the Earth's axis, the Sun, the galactic center, the ancient light. At each step, the speed is larger, the distance to the reference point is larger, and the acceleration needed to maintain the orbit or the flow is smaller. The galactic orbital acceleration, the centripetal acceleration that keeps the solar system on its roughly circular path around the galactic center, is approximately 2 × 10⁻10 meters per second squared. That is 1/5 of a billionth of a meter per second squared. It is 20 billion times smaller than Earth's surface gravity. No instrument attached to a human body has any hope of detecting it. The 4 speeds do not all point in the same direction. This is worth being clear about. The rotation at the equator points eastward parallel to Earth's surface, perpendicular to the Earth's axis. The orbital velocity points along the orbital path, which is tilted at approximately 7 degrees to the plane of the solar system's orbit around the galaxy. The galactic orbital velocity points roughly in the direction of the constellation Cygnus in the plane of the Milky Way, approximately perpendicular to the direction toward the galactic center, and the cosmic microwave background motion points toward Leo, which is in a direction that is not aligned with any of the others. If you added them as vectors, which is the physically correct thing to do, you would not get 4 times any one of them. You would get a net vector that is the sum of 4 components pointing in 4 different directions. The displacement during a single breath is therefore in a direction that has no name in any human language. Not east, not north, not toward any visible landmark. It is a combination of eastward rotation, orbital motion along the ellipse, galactic sweep towards Cygnus, and cosmic flow toward Leo. None of those four is parallel to any other. The net direction is somewhere among all of them, unique to this exact moment in the year, in the orbit, in the galactic rotation, and in the cosmic flow, and it changes continuously because the rotation and the orbit are constantly altering the directions of two of the four components. The cosmic microwave background dipole measurement gives precisely this net vector, incorporating all four motions and everything else stacked above them. When astronomers subtract the solar system's orbital contribution from the dipole to get the peculiar velocity of the Milky Way, and then subtract the Milky Way's motion relative to the local group to get the local group's peculiar velocity, they are unpacking the vector sum one layer at a time. The full unpacking requires knowing each component's speed and direction precisely, which is why each measurement in tonight's story was necessary. The dipole alone gives you the total. To know the parts, you need everything else. And at the same time, in the same breath, the body is at rest relative to the floor. The floor is at rest relative to the building. Both descriptions are correct. Neither overrides the other. They use different reference frames and produce different answers. And the physics says both answers are valid within their frames. The stillness is real. The motion is real. They coexist without contradiction, as they have coexisted in every breath the body has ever taken. The history of tonight's answer covers 4 centuries and dozens of people. Copernicus proposed in 1543 that Earth orbited the Sun, but this was geometry, not proof. Galileo explained in 1632 why the orbit could not be felt the principle of inertia, but this was reasoning, not measurement. Bradley confirmed in 1728 that Earth was actually moving by finding the aberration of starlight that only makes sense if the observer is in motion. This was the first direct measurement. Shapley established in 1918 that the solar system was far from the galactic center, showing that a third motion existed, even before it could be precisely measured. Michelson and Morley demonstrated in 1887 that there was no ether, clearing the way for Einstein's relativity in 1905, which provided the framework in which the speed of light is the same for all observers and constant velocity is invisible in all experiments. Penzias and Wilson found the ancient light in 1964, the reference against which the outermost motion could eventually be measured. Smoot and the Cosmic Background Explorer team measured the dipole in 1992, establishing the fourth speed. Gaia's data, analyzed in 2016, sharpened the galactic orbital figure. None of these people set out to answer the question, how fast are you moving right now? Copernicus was trying to account for the apparent backward loops the planets trace against the stars. Galileo was defending the Copernican system against the objection that a moving Earth should fling loose objects westward. Bradley was trying to measure the distance to a star and found velocity instead of position. Shapley was mapping the size and shape of the galaxy. Michelson was trying to detect the ether wind. Einstein was reconciling electromagnetism with mechanics. Penzias and Wilson were calibrating an antenna. Smoot was looking for the primordial temperature fluctuations, and the dipole, the record of our motion, was the largest signal in his data, and the thing he had to remove before he could see what he was actually looking for. The question was assembled retroactively from work aimed elsewhere. Each person added one piece in pursuit of something else, and the picture emerged slowly, without design, as each new measurement forced a revision of the previous one. There is something worth pausing on in the fact that all 4 of these motions were operating fully throughout every moment of human history that preceded their discovery. When the first humans looked up at the stars and tried to make sense of the lights moving across the sky, the Earth was rotating beneath them at over 1,000 kilometers per hour, orbiting the Sun at over 100,000, sweeping around the galaxy at over 800,000, and flowing through the ancient light at over 1,000,000. None of it was known. None of it was suspected. The people who built Stonehenge, who tracked the solstices, who named the constellations and told stories about them, all of them were moving at these speeds, in these directions, and had no way to know it and no reason to imagine it. The motions did not wait to be discovered before they began. They did not become real when Bradley measured the aberration or when Smoot mapped the dipole, they were exactly as real and exactly as fast in the year 10,000 before the present as they are tonight. The discovery did not change the universe. It changed only what a small number of people on one planet knew about the universe. The four speeds were a fact about the world long before they were a fact in anyone's mind, which is the ordinary condition of almost everything that is true. The universe does not arrange itself to be noticed. It simply does what it does, at whatever speed it does it, and occasionally something inside it develops the capacity to measure a small part of what has been happening all along. This is how physics works. Not by revelation, not by a single grand insight, but by the slow accumulation of careful measurements that gradually correct and extend each other until the picture is clear. The picture is currently this: one rotation at 1,670 kilometers per hour, one orbit at 107,000, one galactic sweep at 828,000, one motion through the ancient light at approximately 1,300,000, all simultaneous, all real, all from inside the frame, invisible. There is one further thing. The universe is not done being measured. The numbers are well established, but the precision will improve. Gaia's full data release will refine the galactic orbital speed further. Future missions will map the peculiar velocity field of the local universe with greater precision. The exact contribution of the Shapley supercluster and other distant structures to the local group's motion is still being worked out. The picture tonight is the best current picture. It is not the final one. This is not a reason for uncertainty about the broad outlines. The rotation, the orbit, the galactic speed, the cosmic microwave background speed, these are not going to change significantly. The refinements will come at the level of precision, not at the level of the picture itself. The picture is not finished, and it will not be finished in any of our lifetimes. There will always be another layer to measure, another structure beyond the last one, another decimal place to sharpen. That is not a deficiency. It is simply the condition of looking at a universe far larger than the instruments that look at it. 1 million kilometers per hour is approximately right and will remain approximately right. The measurement is sound. What remains to be sharpened is the third and fourth decimal place, and the precise decomposition of the outermost speed into its component flows the details, not the structure. The room is dark. The body is at rest. In every sense the body can know. There is a particular quality to the dark at this hour. The noise of the earlier evening has settled. The sounds outside, traffic, voices, the ordinary sounds of the day have either stopped or reduced to a background that no longer asks for attention. If you have been listening for 2 hours or more, the material has had time to accumulate in the way that long listening allows, not as a list of facts held in working memory, but as a texture, a revised sense of what is happening in the room at this moment. What is happening in the room at this moment is this. Somewhere beneath this room, the ground is moving at whatever speed the latitude dictates, somewhere around 1,200 kilometers per hour. For most of the people who listen to channels like this, in the northern hemisphere, in a city, the planet has been rotating at approximately that speed since it formed 4.6 billion years ago. The rotation has slowed slightly. Tidal forces from the moon have been draining angular momentum from Earth's spin for billions of years, lengthening each day by fractions of a millisecond per century. The day was 6 hours long when the planet was new. It is now 23 hours and 56 minutes, measured against the stars. It is still lengthening, at rates too small to notice in a lifetime, but real, and confirmed by the growth rings of fossil corals that recorded the length of the day hundreds of millions of years ago. In Paris, 67 meters of wire hangs from the dome of the Pantheon, and an iron ball swings from it, a reconstruction, the original's cable having broken in 2010, but a reconstruction built to the same specification. The floor rotates slowly beneath the pendulum about 1 degree every 5.5 minutes at that latitude, and the ball does not care. It simply hangs in space, anchored by inertia to the frame of the distant stars, while the building and the city and the country turn under it. Léon Foucault, in January of 1851, sent a note to a small group of scientists that read, "You are invited to see the Earth turn." He built the demonstration in his workshop first, then at the Paris Observatory, then at the Pantheon before a public audience. The reaction, by contemporary accounts, was silence. People stood and watched the floor separate from the swing of the pendulum, and they understood what they were seeing, and there was nothing to say. The invitation is still open. Anyone who goes there, today, and watches for half an hour, will see the Earth turning beneath a weight that hangs perfectly still. The planet is also orbiting the Sun, 107,000 kilometers per hour, along an ellipse that is nearly circular, completing one loop every 365 and a quarter days. James Bradley established this observationally in 1728 from a star in Draco that shifted in the wrong direction. He spent 2 years not understanding the shift. A wind vane on the Thames during a sailing trip gave him the answer. Light, arriving at a moving telescope, must be caught by tilting the tube slightly in the direction of motion, just as rain must be met by tilting an umbrella in the direction of walking. The tilt is the aberration. The aberration is the proof the orbit has been real, and measured, and confirmed many times since. And it runs at 107,000 kilometers per hour, and it will continue to do so for several billion more years until the Sun expands and the inner solar system rearranges itself. The solar system is orbiting the galactic center, 828,000 kilometers per hour, around a point 26,000 light-years away, in the direction of Sagittarius. One loop every 225 to 250 million years. The solar system has been doing this for approximately 20 loops since before the Cambrian explosion, since before complex animal life existed on Earth, since before the supercontinent Pangaea, since before anything we would recognize as the world was assembled. It will continue for as long as the galaxy exists. The galactic center is marked by Sagittarius A star, a black hole 4 million times the mass of the Sun, which the Event Horizon Telescope photographed in 2022, a ring of glowing gas around a shadow, the size of a solar system, 26,000 light-years away, the anchor of everything that orbits, and the entire assembly, the planet, the solar system, the galaxy, the local group, the Laniakea supercluster, and everything flowing with it is moving at approximately 1,300,000 kilometers per hour, relative to the oldest light in the universe, toward the constellation of Leo. This was measured by the Cosmic Background Explorer, launched in 1989 by a team led by George Smoot, who had proposed the measurement 15 years earlier and spent those years building it. The ancient light shows a temperature difference of 3.36 millikelvin between the hemisphere the solar system is moving toward and the hemisphere it is moving away from. That difference is the measurement. It has been confirmed by the Wilkinson Microwave Anisotropy Probe and by the Planck satellite. It is not going to change. None of it can be felt. Galileo understood why in 1632. Constant velocity, at any speed, is physically indistinguishable from rest for any experiment conducted inside the frame. The body's instruments are perfectly designed for their purpose, navigating a world measured in meters and seconds, and perfectly blind to the motion those instruments share. There is no force to detect. There is nothing pushing against anything. The motion is real. The silence is also real. Both are true, simultaneously. The cosmic microwave background radiation is in this room right now. It is passing through the walls, through the ceiling, through the body, in every direction. It is faint, 2.7255 Kelvin, a temperature at which objects glow only in the microwave part of the spectrum, completely invisible to ordinary senses. There are approximately 400 photons from the background radiation in every cubic centimeter of the room. They arrived from every direction, having been traveling for approximately 13.8 billion years, since the moment the plasma of the early universe cleared and light was freed to travel. They entered through the walls and will exit through the opposite walls and continue outward into the universe, slightly cooler now than when they entered, cooled by the ongoing expansion. They have been traveling for 13.8 billion years. They have a comparable span ahead of them before the universe's expansion. Continuing to accelerate will have stretched them to wavelengths too long and energies too low to interact with anything at all. At that point, the background will be, for practical purposes, gone, its temperature dropping below any meaningful threshold. The photons spread so thin across a universe so large that they will constitute a field of effectively zero energy, and the universe will have lost the last faint trace of its beginning. That is a long time from now. There is nothing to do about it tonight. It is worth noticing what kind of fact this is. It is not a fact that asks anything of the person who learns it. Knowing that the body is moving at over 1,000,000 kilometers per hour relative to the oldest light in the universe does not change how the body should be cared for, or what it should do tomorrow, or how it should feel about anything. It is not a lesson. It carries no instruction. It is simply true, in the way that the distance to the sun is true, or the number of bones in the hand is true, a fact about the actual condition of things, available to anyone who wants to know it, indifferent to whether anyone does. And there is a quietness in that. The universe is not performing these motions for an audience. It is not moving fast to impress, or slowly to soothe. The speeds are not large in order to be astonishing. They are simply what falls out of the initial conditions and the laws, the leftover momentum of a galaxy that formed from collapsing gas, of a solar system that condensed from a fragment of that galaxy, of a planet that accreted from a fragment of that solar system. Every layer of motion is inherited from the layer above it, handed down from the formation of structures far larger and far older than anything human. The body did nothing to acquire these speeds. It received them, the way it received the carbon in its cells and the iron in its blood, from processes that ran to completion long before it existed. The four speeds continue. The rotation continues, as it has for 4.6 billion years. The orbit continues. The galactic sweep continues, 20 times around and still going. The motion through the ancient light continues, carrying the local group toward Leo, toward the Shapley supercluster, along a gravitational flow that has been in place since the early universe, and will persist for as long as these structures exist. And the breath continues. The slow, automatic rise and fall of the chest, carrying the body through approximately 4 more seconds of each of those motions with every cycle. 1.3 kilometers of rotation, 120 kilometers of orbit, 900 kilometers of galactic sweep, several hundred more through the ancient light. None of it requires anything of the body lying here. The body is a passenger in all of it, as it has always been, as it will remain. The physics does not consult anyone about these motions. The speeds do not change because someone finds them difficult to hold. They continue because they have always continued, because the initial conditions of the solar system and the galaxy and the universe propagated forward in time to produce this particular moment, this particular room, this particular speed toward Leo, and they will continue to propagate forward long after the room is gone and long after the speed is no longer measured by anyone. The body that began tonight believing itself still is the same body. Nothing has changed that the body can detect. What changes, if anything changes, is not the facts, but the relationship to them. The stillness the body reports is real and correct, for the scale the body was built to navigate. The motion the physics describes is equally real, in a sense that took pendulums and wind vanes and globular clusters and a satellite and 4 centuries of careful work to reach. Both are true. They do not compete. They simply describe different frames, and the body is in all of them at once. The oldest light in the universe passes through the room. The floor turns slowly beneath a pendulum in Paris. The ground moves at 1,200 kilometers per hour under the body, that is, by every measure the body has perfectly at rest. Good night.